All right, welcome to Physics 2425, Lecture 10, Newtonian Gravitation. We're going to be looking more specifically about the macroscopic understanding of gravitation. We will not delve into relativity or the Higgs boson or anything quantum related. We still really don't understand gravity. New experiments are always coming up with new things and new interpretations. But what we know is, for our purposes, Newtonian gravitation is a good model that can explain, and we'll be delving particularly into looking more at orbit mechanics and how this applies to like our solar system and satellites and so forth. Newton's law of gravitation tells us that the gravitational force is related to two masses pulling on each other. And the gravitation formula here tells us that this is an inverse square law, so that distance is a huge factor, so that as your objects get further and further away, you're going to end up with smaller gravitational forces. So you get this inverse square relationship. So your gravitational force does decrease pretty dramatically with distance. So some things about this equation, you do have to assume that the objects are spherical and they have basically no volume. It's kind of an approximation that we make, but it works. But the objects kind of get boiled down to point masses, where the point mass is treated to be at the center of whatever the actual object is. Newton's third law says that the force of attraction of object 1 on object 2 is equinox to the force of object 2 on object 1, which agrees with universal gravitation. So when you look at this force, we have this inverse square law, as I mentioned, so that as your radius approaches infinity, gravitational force approaches 0. But in order to actually escape from a gravitational field, you would have to get infinitely far away, because there's always going to be some amount of that gravitational force. Now, actually, inside Earth's radius, it's a completely different function. It's actually a nearly linear function, so that there is no gravitational force at the dead center. And that's because all of the mass of the Earth would be pulling you from different directions. So all the gravitational forces would cancel out. And then it actually increases linearly until you get to the surface. So you do actually lose weight by going down into a cave that is underground. Is kind of spherical. It's not a uniform density. The density greatly increases depending on where you are at kind of with your materials. So your inner core is very dense and less so outside. So we generally just assume that the interior of the Earth is a solid uniform sphere for our purposes, with an average density, if we're actually going to be doing math with it. Now, as I mentioned, if you go inside the Earth, you actually get a different function for the behavior of gravity. So if you wanted to derive that function, essentially what you picture is, if you are standing somewhere inside the Earth, so say you dug a really big hole and you could stand at that point on the Earth at some radius little r that is smaller than the big R, then basically what happens when you look at the gravitational forces, if I picture this piece of mass right here and what it's doing, it's pulling me in with some sort of gravitational force. If I picture this little mass right here, it's actually pulling me in a different direction. And this mass is pulling me in a different direction. And amazingly enough, what happens is the equivalent of all of this mass that is outside your radius, those gravitational forces completely cancel themselves out. So we only need to worry about the mass that is inside of the radius r. So essentially, what we do is we still use our gravitational force as being equal to g m1 m2 over r squared. But we're looking at not the full mass of the Earth, we are looking only at the portion of the mass of the Earth that is inside of that radius, because the part that's outside is canceled out. So we basically need to figure out what is M prime. M prime is the mass that is inside of radius r. What we can do is we can basically assume that our density is uniform. So we assume that our density is mass over volume. Our density is going to be mass, volume of sphere is 4/3 pi r cubed. So the whole Earth has a mass big M and a radius big R. And then we're going to look at some other radius that has some sort of mass M prime and a volume of 4/3 pi little r cubed. So when you simplify this down, the 4/3 and the pi cancel. So our mass M prime is going to be M over big R cubed times little r cubed. So our gravitational force is going to be G M1. M2, we're going to assume M1 is U. So M2 is the mass of the Earth. So that is going to be our M prime. So M over big R cubed. And then r squared, we are still at this little r radius squared, so that is the lowercase r squared. So this r squared in the bottom is going to cancel out one of those r's, so you get Fg is equal to G M1 M all over r cubed. So this is a different function. Now, this M is the mass of the Earth, this M is the mass of U, and then we've got an r here right there. So you got the big R cubed here. So this stuff here is all constants. So when you're inside of the Earth, our gravitational force is proportional to R, which when you graph Fg and R, you're going to get a straight line. So inside the Earth is linear. Outside the Earth, your Fg is proportional to 1 over r squared. So kind of fun. And both functions get the exact same value at the surface of the Earth, which makes sense. There's no discontinuity. Now, how does this change our view of potential energy? To do this derivation, what we're going to do is we're going to look at 2 different points. We're going to look at a position R1, and then we're going to look at some other position R2. So by definition, for conservative forces, our force is equal to negative du dx. Or in this case, we're just going to use dr. We're going to use r as our axis. R starts r equals 0, and then goes out to r equals infinity. So Fg is actually in the negative direction. So if I plug in my force is going to be negative G M1 M2 over r squared is equal to negative du dr. So if I want to find du, I'm going to get dr on the other side. So I'm going to get that, and the negatives cancel. So I get G M1 M2 over r squared is equal to du over dr. So du is equal to G M1 M2 over r squared dr. And then you can integrate this. We're going to integrate from R1 to R2 and between U1 and U2. So we come over here. The integral of du is just going to be u. So we're going to get u evaluated from U1 to U2 is equal to G M1 M2. And those are constants. And I'm actually going to change the 1 over r squared to the r to the negative 2 dr. And that's going to get integrated from R1 to R2. That's going to make it easier to see the power rule. I'm going to pull out my constants. Over here on the left, I'm going to sub in U2 minus U1 for my limits. G M1 M2. And then the integral of r to the negative 2, I have to increase the power by 1. So that's 1 over negative 1, r to the negative 1, evaluated from r1 to r2. So I get u2 minus u1 is equal to negative g m1 m2 over r2 minus a negative g m1 m2 over r1. So if we look at this, we have u2 minus u1. So if I kind of compare the left side with the right side, this right here has to be u2, and this right there has to be u1. So in general, we can define our gravitational potential energy as being negative g m1 m2 over r. And you can use just the general definition of a conservative force to find that. For example, if we were looking at the mass of the Earth, you would sub in mass of the Earth, little m would be the mass of the object. But this negative is like the most confusing part of this whole thing. Our potential energy is actually always negative under the assumptions of kind of this integration. So how does that work? Well, if you were to graph this function, once again, it's only going to work when you're outside of the radius of the Earth. You can find what's going on inside if you use the g m1 m over r cubed r for inside the Earth. And you could do that same derivation where you would set that equal to negative du dr. And you could then define what potential energy is going to be inside of the Earth. But for outside of the Earth, what you get is you get that your UG is equal to negative g m1 m2 over r. And this negative 1 over r function is going to have a maximum negative value when you're close to the surface of the Earth. And it's going to increase, but get closer and closer to 0 as r approaches infinity. So that when r is infinity, u is actually 0. But 0 in this case is a very large number. Mathematically, this is an increasing function. Mathematically, if you have a positive slope, you have an increasing function, which is consistent because we know when I toss a ball up in the air, its potential energy increases. So if I were to launch a rocket from the Earth into space, its potential energy has to increase. But in this case, it increases towards 0. It's a mathematical quirk. And so it can kind of boggle your mind. So the more negative the number is, the smaller the potential energy. The closer to 0 your number is, the bigger it is. But your potential energy can actually never be positive under this model. So what I want you to do right now is pull up the PowerPoint and watch this video on Newton's thought experiment. It's going to give you a good introduction into how we were able to extrapolate kind of the motions of the planets and satellites without ever having been able to leave the surface of the Earth. This is kind of Newton's, not really the apple, but he used a cannon kind of as this. So pause the video, pull up the PowerPoint, watch that video, and then come back. So if you watch the video, you fire this cannon. If you don't fire it very hard, it's going to come and it's going to hit the Earth. If you fire a little further, it's going to hit the Earth further. But at some point in time, you can actually get the object into orbit. But there's only one particular speed that will get you a perfectly circular orbit. That perfectly circular orbit is curve 4. The ones that I think here that are 1 through 3, these are actually these are ellipses, and they're ellipses with the Earth being at one of the focal points. 5 is an elliptical orbit that also has the Earth at a focal point, but it's actually at the opposite focal point. And then 6 and 7 are what they call open orbits. They are trajectories that are parabolic and hyperbolic. These are all conic sections. So they all relate to basically the speed of the orbit. So we already did some orbit mechanics, assuming that we had a circular orbit. But everything that we do with orbit mechanics can work in elliptical orbits as well, just with some modifications. So when you are looking at the circular orbits, this is just a review, kind of a refresher. We assume that the gravitational force is the centripetal force, and therefore the centripetal acceleration is the acceleration due to gravity. So you would set the gravitational force equal to the centripetal force. Because in an orbit you still have a gravitational force, you still have weight. When our acceleration is less than g, you are going to feel weightless, because our feeling from weight actually comes from the normal force that we are feeling. Up on the ISS, they do not have an acceleration that is equal to 0. But what happens is they're falling at the same rate as the space station around them, so there's no normal force, so they cannot feel the weight, so they feel weightless. So we could actually figure out the acceleration due to gravity on the ISS using those circular orbits. When we're working with circular orbit problems, we're going to assume that our gravitational force is equal to our centripetal force. Our gravitational force is g. I'm going to use the little m for the mass of the ISS, me for the mass of the Earth, and then r squared. And that's going to equal our centripetal force, which is the mass of the ISS, little m, times our centripetal acceleration. Because when we are in orbit, the only force acting is gravity. Gravity is the centripetal force, so that means our only acceleration is centripetal acceleration. So the centripetal acceleration that I'm looking for is the answer. So the mass of the ISS actually cancels out. So our acceleration that we're looking for is g me over r squared, but we have the radius of the Earth plus the orbital height that we're at squared for that r, because we're the radius of the Earth plus some additional height away from there. So we can then plug in g is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. The mass of the Earth is about 6 times 10 to the 24th kilograms. The radius of the Earth is 6 times 10 to the 6 meters. Plus 400 kilometers is 400 times 10 to the 3rd meters. And that gets squared. So when you plug in our centripetal acceleration, is only about 9.78 meters per second squared. So even though they're up in space, they still have nearly the same acceleration as on Earth, because they really haven't gotten very far away. To find the orbital speed is the next one. So in this case, for the orbital speed, we take it one step further. We take our gravitational force equal to our centripetal force. Our gravitational force is g m mass of the Earth over r squared. Our centripetal force is m. We're going to use v squared over r. So one of those r's cancels. The little m for the mass of the ISS cancels. So our orbital speed is the square root of g times mass of the Earth over the radius, and that radius is once again radius of the Earth plus the orbital height. So plugging in numbers, we get 6.67 times 10 to the negative 11 Newton meters squared per kilogram. The mass of the Earth, 6 times 10 to the 24th kilograms, over the radius of the Earth, 6 times 10 to the 6 meters, plus 400 times 10 to the 3rd meters. And we get our orbital of around 7,900, and let's see, what is that, about 8 meters per second. So it's flying through space. And actually, you can see it at night. You can actually see it go by. You can find trackers for the ISS, and it'll tell you exactly when it's going to be overhead. But it's only visible for 30 seconds or so before it dips below the horizon. It's moving so fast. It's pretty crazy. All right, so in this example, we're going to look at lifting a satellite from one circular orbit to another circular orbit further out. So if you think about what's going on in this situation, you have an orbit that is at a particular radius, and you have the mass moving, satellite here moving with some sort of speed. So it's going to have potential and kinetic energy at that circular orbit. So if I'm going to do work in order to lift it into a higher orbit, not only do you have to change the potential energy, you also have to change the kinetic energy, because every single orbit, every circle has one velocity at which you can go in that perfect circle. So one of the easier ways to kind of solve this problem is just to understand that our work is going to be the change in energy, and look at our energy at each part. So instead of putting together one huge equation, we're going to figure out our energy at the first radius, which is based on kinetic and potential. And then we're going to look at our energy at the second radius. So when we use our kinetic energy, that's just going to be 1/2 mv squared. So whatever the speed we're going at the start. And our potential energy is now the negative g m1 m2 over r1, not squared, sorry, it's just r1. We have r, what we don't have is the speed. And our gravitational force is our centripetal force. Our gravitational force is g m1 m2 over r squared. And our centripetal force is mv squared over r. I'm going to just use m1, cancel those out, and the r gets canceled there. So we end up with v squared equaling g m2 over r. And this m2, in our case, since we're orbiting Earth, that is going to be the mass of Earth. And m1 is going to be the mass of our satellite. So m1 is 100 kilograms. m2 is 6 times 10 to the 24th kilograms, approximately. So I'm going to give this m here a little subscript m1 because that is going to be the mass of our satellite. So I'm going to sub in this v squared here. So I'm going to get E1 is going to be 1/2 m1 g m2 over r, and that's going to be an r1 in this case, minus g m1 m2 over r1. So this is kind of cool, actually, because these are nearly identical to each other, except for the kinetic energy term actually has a 1/2 in front of it. So we can combine these terms, and we get that our energy is equal to negative 1/2 g m1 m2 over r1. Or we can write that as negative g m1 m2 over 2r1. So that's going to be our energy at the start. Well, our energy at the end is going to have the same format, except for we're going to have a different r. So our work is the change in energy. So E1 is this guy. E2 is going to have the same form, but it's going to be negative g m1 m2 over 2 times r2. So our work is the change in energy, which is E2, negative g m1 m2 over 2r2, minus our, well, we're doing E2 minus E1, right? Minus a negative g m1 m2 over 2r1. So we can kind of combine those terms together by pulling out a g m1 m2 over 2. And basically you get a negative 1 over r2 plus a 1 over r1. So you just switch those around, G M1 M2 over 2 times 1 over R1 minus 1 over R2. Okay, and that's going to be our equation for work. So we end up with G being 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. M1 is 100 kilograms. M2 is about 6 times 10 to the 24th kilograms, just being approximate here with the mass of the Earth. Okay, that's divided by 2. Now, these R's, these are just above Earth's surface. So R1 is actually the radius of the Earth plus 100 kilometers. R2 is the radius of the Earth plus 300 kilometers. R2 is 400 kilometers. So you do have to be careful there. So R1 is going to be, our radius of the Earth is about 6 times 10 to the 6 meters. And then we convert kilometers into meters. That's going to be 300 times 10 to the 3rd meters. And then we're going to subtract 1 over R2. So we're going to get this 6 times 10 to the 6 plus this time 400 times 10 to the 3rd meters. So we're going to plug that all in. And we end up with the work being done equal to about 9.9 times 10 to the 7th joules. So another common example we use is escape speed. So the escape speed is the minimum speed needed to escape an object's gravitational field. So we want to get kind of a general equation for escape speed. So we need to understand what this minimum speed to escape needs. First of all, so say you are here like on the Earth. To escape Earth's gravitational field, you have to get where the gravitational force is equal to 0. Well, our gravitational force is an inverse square law, and it has an asymptote. As R approaches infinity, the gravitational force goes to 0. So what that means is in order to escape, you have to get infinitely far away. So one of the assumptions we have to make is that we need to have a speed, whatever this V escape is that it has to have at the surface right here. It has to be fast enough so that it can actually reach a distance of R equals infinity. And as it moves further away, it's going to gain potential energy. And it's going to lose kinetic energy. So there are lots of speeds that will be able to get me to a distance of R equals infinity. But I want the minimum speed. So the minimum speed basically says that as I gain potential and I lose kinetic energy, I want to reach R equals infinity with just having run out of kinetic energy, so that it will basically stop there at R equals infinity and it will not come back. If you go any slower, it will not have reached the point where the gravitational force is 0 and it'll start getting pulled back in. If you go faster than the minimum speed, you will have kinetic energy, and the faster and faster you go above the escape speed, the more kinetic energy you have. So this escape speed is the minimum speed that you need to get around and get out of that orbit. So that kinetic energy has to be 0, but don't forget our gravitational potential energy is negative G M1 M2 over R. It's an inverse relationship, but it's a negative inverse relationship. So our potential energy as R approaches infinity actually goes to 0. So we're going to have kinetic energy equals to 0 and potential energy equals to 0 when we reach infinity. So that's going to be our big assumption. So whenever you do escape speed, the assumption is that our kinetic energy is going to be 0 and our potential energy is going to be 0 when we reach R equals infinity. This is really an energy conservation problem. So we're going to have at our original location, okay, we have a satellite in a circular orbit of radius r from the center of the Earth. So we're going to ignore like the height and the radius of the Earth itself. So we're just going to assume that our satellite is out here and it is in some sort of orbit, okay, at this radius of r. We have the mass of the Earth here. In order to be in that circular orbit, it has to be moving with some sort of v. And what we want is we want for that v to be v escape. So that here at this original position, we are going to have some kinetic energy and some potential energy at the start. And we know to escape, we need our kinetic energy to be 0 and our potential energy to be 0. So we're going to assume that those are our two initial cases. So the first case is when we're in the orbit. The second case is when we have escaped. So I'm going to say that my K1 plus my U1 has to equal K2 plus my U2. And we're going to assume, and always show this, that K2 is 0 and U2 is 0. So we're going to set both of those equal to 0. And then my K1 is going to be 1/2 m v squared. My potential energy is negative g m1 m2 over r squared. No, not, I always do that with the square. It's not a square, just r1. So I'm going to call this one m1, and m2 I'm actually going to call m2. I'm going to call mass of the Earth. Here, let's erase that. Make that. I'm just going to call that one me. So this has to then all just add up to 0. So in the previous example, we used our circular motion equal to our centripetal force to solve for our speed. But that gives us our orbital speed. That gives us the speed that we need to maintain that circle. Our escape speed is going to have to be higher than that. So instead of making this substitution this time, we actually have to solve for this v. So to do that, I'm going to move the potential energy to the other side. So I'm going to get 1/2 m1 v escape squared is equal to g m1 mass of the Earth over r1. So since I have m1 on both sides, I can cancel the m1, which actually means that as long as I'm outside the Earth's atmosphere, the mass of the satellite itself doesn't affect the escape speed. Now, the work that it would take to get to that escape speed would be dependent on mass, but the actual escape speed itself does not depend on mass. And then I'm going to multiply the 2 to the other side, so we get v escape is going to be 2g me over r1, and then I can take the square root. So this is my escape speed. And that r is going to be whatever this radius is here. So I guess based on my variable definitions, I don't need that r. But that is going to be that one, sorry. So that's going to be my escape speed. Now, let's go back and take a look at this orbital speed and do that derivation again. So you get g m1 mass of the Earth over r squared is equal to mv squared over r. That's going to be our m1 again. So the mass cancels out here. One of the r's cancels out. So we get that that speed is the square root of g mass of the Earth over r. So that's going to be our orbital speed. So this guy is the orbit. So that's the speed that you have to go at whatever this radius is here in order to go and keep going in that perfect circular orbit. And notice, this is really cool, that those equations are very similar. So that v escape is the square root of 2 times v orbit. So that's really a cool kind of result here. So you just have to go the square root of 2 times faster in order to reach that escape speed. When you're looking at those elliptical orbits, which is what all objects are actually doing, it's hard. You can't really get that perfect circular orbit. You end up being able to basically describe the circular orbit as a special case of an ellipse. So this kind of animation here shows the different elliptical orbits. The red one is your pure circle, and that one goes at a constant speed around. You can see that all of these elliptical orbits move faster in this area where you are closer to the sun, and they slow down out as you get further away. So that's really what all of our planets do. Now, if you go through, you can actually play around with the gravity and orbit simulation. You're actually going to use this for your lab, so I'm not going to take the time to go over this. But the idea is that if you set your object into orbit, there's only one speed that gives you that perfect circular orbit. So in your lab, you're looking for those circular orbits. So at every particular radius, you're going to have to figure out what speed it is that gives that perfect circle, because every other orbit is going to give you an ellipse. And therefore, you won't be able to apply your circular motion. In order to describe elliptical orbits, Kepler came up with these laws. Now, Kepler came before Newton, so we did not have the concept of gravitation. Kepler used astronomical data and geometry, basically, to come up with his laws of elliptical orbits. What's amazing is once Newton came up with gravitation, he was able to go through and prove that Kepler's laws are actually correct and that all of our planets are actually moving in elliptical orbits. So Kepler's first law states that each planet moves in an ellipse with the sun at one focus. So an ellipse has 2 focal points, with your circle being the perfect case when both focal points are in the exact same location. So the sun, whatever they're calling a body here, this could be like the sun, is at one of those focal points. So we have some terminology that we have to learn. So the long axis is called the major axis. The short axis is called the minor axis. So we give variable names to half of the major axis. So that half the major axis distance we call the semi-major axis. Semi for half, and we give that the variable a. And then the minor axis, when you take half of that right here, that we give b, for the semi-minor axis. Now, you can then do some geometry type stuff with those. So you can actually create a triangle here. And then there's also some distances that you would have to deal with when relating over to the distance to the sun. But what you can do is you can basically derive a value for how elliptical the orbit is. So that's what eccentricity is. Eccentricity is a measure of how elliptical the orbit is. So E is 0 for a circle, E would equal 1 for a line. So if those focal points got so far apart that the planet could only oscillate back and forth between those points, that would be an eccentricity of 1. So you can calculate the eccentricity by using the values for the semi-minor axis and the semi-major axis. Okay, that's kind of cool. Now, we spent all this time talking about circular orbits, and now here I'm coming and talking about elliptical orbits. So why did we even bother with the circular orbits? We bother with the circular orbits because the orbits of the planets are actually really close to being circular. And we know that by their eccentricity values. For example, the eccentricity Earth right now is approximately 0.02. That's really close to 0. It's been higher. The eccentricity of the Earth does oscillate. That's part of what causes climate variations. It is really close to being circular. The only planet in the solar system that cannot be well approximated is actually Pluto, and that's part of the reason why it's not actually a planet anymore. Pluto's called a dwarf planet, and there are other dwarf planets, Ceres, which is an asteroid, Makemake, Haumea, and so forth, are out in the Kuiper Belt. They all have much more elliptical orbits because their dominant gravitational force is not the sun. They're influenced by other things. But all of our classical planets, Mercury through Neptune, can all be described fairly well within circular orbit, which is kind of cool. So Kepler's second law is kind of odd. It says a line from the sun to a given planet sweeps out equal areas in equal times. So when you look kind of here, what we're talking about is if this is T1 and this is T2 and our planet moves, okay, and this is, say, 30 days, so it's like a month. If this is also 30 days, then this area and that area have to be the same. You could use conservation of angular momentum to prove this along with some geometry. So in order for it to take 30 days to go this distance and 30 days to go that distance, the speeds can't be the same. And so that's kind of what this animation shows. So this animation is showing that the planet is going to move faster when it's closer to the sun and slower when it's moving further away. But those areas are actually equal. And that's related to kind of the orbital speed. So he was able to figure this out without understanding gravitation and so forth. Then Kepler's third law tells us that our period squared is proportional to a cubed. And a cubed, once again, is that semi-major axis. And period is the time it takes to go through a full orbit. Now, you can do this derivation of Kepler's third law assuming a circular orbit. So basically, you assume that your gravitational force is your centripetal force. So you get G m1 m2 over r squared is equal to m. I'm going to use the m1 v squared over r. Now, I'm going to make m1 the planet. So m2 is going to be the Earth. Or sorry, not the planet, the sun. m2 is the sun. So m1 actually gets canceled out. So the mass of the planet gets canceled out. Your r gets canceled. So you get your g m2 over r is equal to v squared. Now, we've seen this before, but I want to relate period. So I think about if I'm going in a circular orbit, that the period is the time it takes to go through one orbit. So one orbit with a radius of r has a distance equal to 2 pi r. You go through the circumference. And then the time is the period. So if you're going to constant speed, speed is distance over time, which is going to be 2 pi r over the period. So we can replace that orbital speed with the 2 pi r. So gm2 over r is going to be 2 pi r over the period squared. Now, if you do some algebraic rearranging of that, basically what you get is you get this exact equation right here, but instead of a, you get an r. So you can actually derive Kepler's third law for the special case of the ellipse being a perfect circle. So you're not responsible for being able to do this in elliptical form, but you should be able to derive it in circular form. It's not very difficult to do because we're just setting the gravitational force equal to centripetal force with the addition of the orbital speed being circumference over period. What this says is that if you were to graph the cube of the semi-major axis on one side and the square of the orbital period, you get a linear graph. And when you do that and you cube the semi-major axis for all of the planets, even Pluto, and square the orbital period for all of the planets, they lie very close on this line, which is pretty crazy. So Kepler figured this out without having any of these equations. We didn't have equations for universal gravitation. Newton hadn't come up with them yet. So he just did basically linearization. He figured out by kind of playing around with the variables that plotting the cube of the semi-major axis and the square of the orbital period gives you this linear graph. And then once we had gravitation, we were able to do cool things. For example, not quite the same graph. You'd have to actually plot period squared on the y-axis and a cubed on the x-axis. But when you do that, the slope of that graph, if this is on the y and that is on the x, then this guy right here is your slope. So your slope of that graph would equal 4 pi squared over g mass of the sun. So you can actually use this equation to find the mass of the sun. So mass of the sun is going to equal 4 pi squared over g times the slope of that graph. And so that will actually allow you to find the mass of the sun. Now, in order to do this, you would have had to know g, and g wasn't found until long after Newton, that universal gravitation constant. So you would have to know that in order to do this. But this is one of the ways that we actually figure out the masses of other planets, the masses of... All right, so looking at an example of Kepler's third law, we have the moon that orbits the Earth every 27 days. We want to determine the average distance between the Earth and the moon. So we're going to use Kepler's third law here. We're looking at the average distance, so really we're assuming that our A is approximately equal to R, okay, so the radius there. We're not looking specifically at the semi-major axis, we're really just approximating as a circle. So period squared is equal to 4 pi squared A cubed over GM. In this case, that M is the mass of what's being orbited, so that is going to be the mass of the Earth. We then solve for A. Well, A cubed is going to be period squared G mass of the Earth over 4 pi squared. So then you raise all of that to the 1/3. And that's going to give us RA. So our A is going to be period squared G mass of the Earth over 4 pi squared, all raised to the 1/3. So plugging in, period is in days, 27 days. We need to convert that into seconds. We have to be in SI units. So 1 day is 24 hours. 1 hour is 60 minutes. 1 minute is 60 seconds. And that gives us a period that is approximately 2.33 times 10 to the 6 seconds. So we'll plug that in here, 2.33 times 10 to the 6 seconds. Squared, G is 6.67 times 10 to the negative 11 meters squared per kilogram. Mass of the Earth, we're approximating as 6 times 10 to the 24th kilograms, divided by 4 pi squared, and raising all of that to the 1/3. And that gives us the value for A equal to 3.8 times 10 to the 8th meters. And so what's really cool here is that the actual value for the average distance is 3.844 times 10 to the 8th meters. So all we used was the fact that it takes about 27 days for the moon to orbit the Earth. That's the lunar cycle, 27 days. And we were able to, with even just an approximation of the mass of the Earth, be able to get within 2 significant figures the exact value for the distance between the Earth and the moon. That's really awesome. So conservation laws of elliptical orbit. So if you're watching this in the normal sequence, where this is lecture 10, you will not have learned about angular momentum yet. However, it kind of gives you an easier way to solve some of these conservation problems. However, when we are looking at this, you can always use conservation of mechanical energy for anything related to orbits, elliptical orbits. Angular momentum is a little bit easier to solve because the equation ends up being simpler. But mechanical energy is conserved in elliptical orbits because the only force acting is the gravitational force, and the gravitational force is conservative. So therefore, as a planet moves from in a rounded to elliptical orbit, the kinetic and potential energy will transfer back and forth between each other. Angular momentum is conserved whenever there's no net external torque. So like the sun would exert an external torque on the planet, except for the fact that it doesn't actually exert any torque at all because the gravitational force is parallel to the lever arm. So therefore there is no net external torque applied on that system. If you go through and solve these problems, the angular momentum and the conservation of energy are interchangeable. You will get, with numbers, the exact same equations. They just won't look the same. So to wrap things up, there are some additional tutorials here. The Flipping Physics, Universal Gravitation, and Potential Energy is really good. So once again, that's one of the, because it's negative, it's really weird. So that's a really good video. There's some other ones here, some more escape speed practice, some more on Kepler's laws. And if you're interested in kind of the climate dynamics of kind of orbit mechanics, there's a crash course on the Milankovitch cycles and how Earth's orbit around the sun results in natural climate variation, which is kind of fun. So take a look at this. Have a great day.